So this is going to be the second episode of the Algorithms and Data Structures series, and in this video I'm going to explain the most difficult algorithm I had to implement in my entire life. So the reason I had to implement this algorithm, which I copied from SQLite, is because I took the horrible decision of writing my own database, and databases are not precisely easy to write. So yeah, never do that, but I learned quite a few things from that, and that's why I'm making these videos. Anyway, just like in the previous episode, I'm gonna try to put you into context if you don't have the time to enjoy 42 minutes of carefully crafted database lore, but in this case it's gonna be difficult because B-trees are extremely complex data structures, so you gotta bear with me here. So here's what you need to know about databases before we explain anything. Databases have to work primarily on disk, whether it's an HDD or an SSD, doesn't matter. Most of the work is performed on secondary memory instead of primary memory, which is mostly used for caching, because databases need to deal with massive amounts of data, like imagine a 5 terabyte database. That's not gonna fit in RAM. But still, if you want to modify disk data, you gotta load it into memory first, and then you gotta write it back. So we have to work with, let's say, chunks or parts of the data. These chunks are called pages, and they're stored sequentially in a file. They are fixed size, so all pages are either 4 KB, 8 KB, or 16 KB. It's a power of 2. That way, it doesn't matter how big the database is, because we only load a handful of pages at a time in memory. Therefore, the data structures used by databases are heavily optimized to work with these pages. And one of these data structures is the B tree, which is essentially like a tree, like a binary tree, if you want to compare it to something familiar. But it's made of pages. It stores multiple entries in each node, so each node is basically like a sorted array, and it's optimized for disk storage. Another one of the goals of B-trees is to avoid the main problem of binary trees, which is that they can end up becoming a linked list with O of n search time if you insert the keys in order. But B-trees will never do that because they run a self-balancing algorithm, and that's what this video is about. B-trees can be used to store the contents of database tables, so they can basically store individual rows in each page, or they can be used to store database indexes, which are essentially a disk data structure that can speed up searching by a key or check if a key is unique in log of n time, instead of having to do it linearly, which would be inefficient with so much data. So how do these B-trees look like? What's so special about them? Well, each page stores a number of variable length entries. Let's just say these are rows, because from the B-tree's perspective, it doesn't really matter what the entries are, it's just binary data. The B-tree doesn't care at all. The only thing that entries must have is a unique key, because entries must be sorted in ascending order by their key. Additionally, each of these entries has a header that stores a pointer to another B-tree page, and entries always point to pages that contain keys which are less than the key in the entry itself. So if I follow the pointer in the entry with key 4, then I'll get to the page that contains keys which are less than 4. That's how this works. However, the number of children per page is always one more than the number of entries, and the thing is that pointing to the last child of a page is kind of tricky, because you don't have enough entries, so you don't have an entry to put a pointer into. So each page has its own header, where we put a pointer to the last child, which contains keys that are greater than all the keys in the parent. So I think that pretty much covers all you need to know about the B-tree structure. If you want to know more, you can go check the database video. Okay, so let's just insert entries into the B-tree one by one and see what happens. Now, to keep things simple, we're going to assume that B-tree pages are 60 bytes and all the entries are 20 bytes. That's going to make things easier to compute. So at first we create the root node or root page of the tree, and we insert entries into it in order until it's full. In this case, if the page is 60 bytes, we can fit 3 20-byte entries. Now is when things get interesting. So if you want to insert the entry with key 4, the insertion algorithm per se will just insert the entry into the root, allowing the page to temporarily overflow in memory, which means it goes above its capacity. Okay, at this point, the balancing algorithm in question kicks in. We gotta distinguish between the insertion algorithm and the balancing algorithm. They're not the same thing. The balancing algorithm is called at the end of the insertion. In this example, it's called on the root. The root is a special case, so it has to be treated accordingly. The algorithm is going to allocate a new page, which will become the first child of the root, and is going to move all the entries from the root to the new page. That way, we get rid of the special case, because this is not the root page anymore, so we can reuse the same code for all types of nodes. Once we have a normal node, the first step is moving all the entries outside of the page somewhere else in memory, so that the page is not in overflow state anymore. Now the second step is pre-computing a left-biased distribution for the entries and figuring out exactly how many pages we need. So we're gonna run a couple of loops. The first loop goes from left to right and basically says, okay, I can fit 3 entries in the page that we already allocated before, but then the 4th entry must go into the parent. This is gonna be a divider entry, which means we need to allocate a new page. So the first loop is kind of dumb because it leaves one of the pages empty, but then the second loop goes in reverse from right to left and says, okay, this doesn't make any sense, we have to readjust the entries so that the tree is balanced. And as you can see, we have a left bias distribution, which is great for some disk optimizations when the number of entries and pages is uneven. But remember, this was simply a pre-computation. We did not actually move any bytes in memory, nor did we allocate any pages on disk. We just figured out exactly what we need. And once we know what we need, we can actually allocate the missing pages and move all the entries to their new locations, because we don't want to be moving entries back and forth, we only move them once. In this process, we also have to fix all the pointers, because remember that each entry points to a page, and pages themselves point to pages. So after we execute that portion of the code, the algorithm is done, the B-tree is balanced again, and we got rid of all the overflow states. Alright, let's continue inserting keys in here and see how the algorithm performs. For now, there is enough space to insert key number 5 and key number 6. However, once we insert key number 7, the rightmost node will overflow, so we have to call the balancing algorithm on it. And now we can visualize another detail of the algorithm, which is the siblings balancing. In order to avoid allocating new pages when it's not necessary, we're gonna look at the surrounding sibling nodes and see if we have enough free space to fit the new entries. The number of siblings that we look at on each side of the node is configurable, but it's usually going to be 1 sibling per side. So we take the left sibling and then we would take the right sibling as well, but in this case we only have the left sibling. And again, we're going to move all the entries outside of the sibling nodes, this time including the divider from the parent. Then we pre-compute the distribution again, and we distribute the entries including the updated divider, and this time it's more symmetrical, so it doesn't require readjustments. So as you can see, the number of pages has not actually changed. We just redistributed the entries to maintain balance. Okay, what happens now when we insert key 8? Well, again, grab the siblings, move all the entries out, including the divider, and now pre-compute the distribution again. So the first loop will fill the left sibling, insert the first divider into the parent, then fill the second sibling, insert the second divider into the parent, and therefore increase the number of pages needed because we got a new divider. And now the second distribution loop readjusts the entries again. This time we can make it pretty symmetrical because the number of entries can be evenly distributed between all the pages. And now the tree makes sense again. Everything is balanced. Remember though that we first have to compute all these positions and then we do the actual work, because we don't want to be moving entries multiple times. Alright, I'm going to show you an example where we have to recurse, because this algorithm is recursive. Imagine we've already filled up all the nodes using the techniques I've shown you, so at this point we would have a root node with 4 children. Now if we insert key 16, the rightmost node goes into overflow state. So again, check the siblings, we can take 1 sibling from the left, and since we don't have a right sibling, we can take another sibling from the left. That's going to add up to 3 siblings in total. We move all the entries out, including the sibling dividers from the parent, then we compute the distribution again, and we'll get to the conclusion that we need an additional page, which checks out. Then we move all the entries back to their new positions, and we fix all the pointers. But here's the thing, in doing so, the parent overflows, because it goes above 100% capacity. So we gotta recurse into the parent, we gotta call the same algorithm on the parent. And now the special root case will execute again. So we'll allocate a new child page, we'll move all the entries from the root into the new child, then we fall through the rest of the code, which will move the entries out of the child, pre-compute how many pages we need and where each entry should be located, and then it positions all the entries to their new locations. It fixes all the pointers, and now the B-tree is balanced again. So at this point, if you understand how recursion works, you can kind of get the idea on how the algorithm would work with a giant tree that has many levels. You basically call the algorithm on the leaf node, then you call it on the parent, and you keep doing that until you reach the root and you balance everything upwards. Another important detail is that this same algorithm has to deal with deleting from the B-tree. I haven't even mentioned that because I want to keep it as simple as possible, but I'm going to give you a brief overview into how balancing after removing works. So just like before, removing is an algorithm in and of itself, and at the end of that algorithm we call the balancing one that we've been talking about. So the removal algorithm has a couple different cases. The easiest case is removing from leaf nodes. Let's say we have this tree from before, from the last example, and I want to remove key 3. Well, I can just remove it. I don't have to balance anything. Same with key 7. I can just remove it. But what if I remove key 11? Well, I can't just leave the root empty. I'll have to substitute the removed key with either its predecessor in the left subtree or its successor in the right subtree. Let's say we pick the predecessor. In that case, we move key 10 into the root. However, that causes the leaf node to go into underflow state. So overflow is defined as above 100% capacity, which can only happen in memory, and underflow is defined as below 50% capacity. That's not a problem, but we have to avoid underflow nodes where possible to optimize space usage, although sometimes we don't have a choice. But in this case, we can call the balancing algorithm on the leaf node, we grab the siblings, we move the entries out, including the dividers, and using the same distribution computation from before, we figure out that we can fit all the entries in 2 pages only and using only 1 divider, which means we can get rid of the 3rd page, so we can basically deallocate it. Then we fix the pointers in the parent and we're done. But as you can see, the parent is now in underflow state because it's below 50% capacity, which would be in this case 30 bytes. It's only at 20 bytes. So we gotta recurse into the parent. We call the same algorithm on the parent again. And now yet again, grab the siblings, move the entries out, including the divider, and now the distribution sub-algorithm will figure out that it can fit all the entries in 1 single page without any dividers, which means we can get rid of the 2nd child of the root, we can deallocate that page. So now the root only has 1 child and it's pointing to that child from its header because it doesn't have any entries. The root is empty, so we gotta recurse into the root. Calling the balancing algorithm on an empty root is another special case because we can decrease the tree height. We can move all the entries from the child back into the root, get rid of the child, so deallocate the child, fix all the pointers, and now the B tree is balanced again and we've decreased its height. Notice how the root of the tree never moves. The root page always stays the same. That's important for database purposes. Alright, I'm not gonna bore you with this algorithm anymore, I'll just say that it's no doubt the most complex algorithm I have ever written in my entire life. I remember staring at the SQLite source code for hours and hours without understanding a thing. It's very frustrating. And disk B trees are the most complex data structure I have ever written in my entire life. I don't think anything will even come close to that in the near future. At some point I might get into more complex projects, but not for now. So for those of you that have subscribed, this is how the channel is gonna work. I'm gonna upload an MKO video, and then after that, if necessary, I'll upload more videos focusing on specific algorithms and data structures, because that's gonna allow me to get more content out of the same project, because these projects are very complicated to make, they take a very long time. So the next video is gonna be 2nd episode of MKO, so stay tuned for that one.